Okay, hi everyone. Let's see, microphone working? Yeah. Okay, let's go ahead and get started with today's lecture. So in today's class, we're going to be changing topics a little bit. So for the last few lectures, we've been focused on regression problems, and today we will start looking at classification problems. And so we'll see an example of our first classification model, which is called the nearest centroids classifier. And we'll be focusing on classification problems for the next few weeks in the course. Okay, a couple of announcements and reminders. First homework is due tonight at midnight. And again, no late submissions for this homework. We do drop your lowest grade though. Again, submit your PDFs via Gradescope. You can access that via Canvas. I think about 60 of you have already submitted your homework, so great job, and everyone else, good luck. And it's important to make sure for the homework submission that all of your code and answers are visible. We, of course, can't really grade your assignment if we can't see your code and can't see your output. So if you're having any trouble with the PDF submission, do feel free to post on the Ed discussion board. And then the only other announcement today is that the second homework is going to be released early next week. So keep an eye out for an announcement about that. Hoping to get that out to you guys by about Monday. And the first problem on the second homework is going to be about nearest centroids on this MNIST dataset. And we'll cover the topics you need to cover that problem in today's lecture. Okay. So the topics of today's lecture are classification in general. After that, we'll see some techniques for computing feature means and distances that we'll have to use when we run our nearest centroids classifier. And then lastly, we'll very briefly see some methods for evaluating classifiers. Okay, just a couple of reminders. So supervised learning problems, which are problems that we've been looking at so far, are problems where our data comes in X, Y pairs, where the X variables represent some kind of input data. They're the features of our problem. And the Y variables represent some kind of thing we'd like to predict from the features. In regression problems, which is what we've been looking at so far, we're trying to predict some real valued outcome from those features X. So predicting like the price of a house or maybe a time to a specific event. And in contrast, in a classification problem, which is what we're going to be looking at today, we're trying to predict a Y variable that lives in some finite set of K possible values. So, for example, we might be wanting to classify an image of an animal. So our features represent some kind of image. And we might be trying to predict a label for this image. Or maybe our labels live in some finite set. Here, our labels might be, say, cat, dog, or something else. So this is a classification problem with 3 potential labels. In practice, what we often do in order to sort of encode these labels into our computers is that we index our label set by some sequence of integers. So if we have k distinct classes, or k distinct labels in our classification problem, then we'll just use the numbers 1 through k in order to actually encode these labels. So in our image classification data set that we have in this example, we have 3 possible labels, cat, dog, or other. And so we would encode our labels as just the numbers 1, 2, and 3. There's a bit of an exception here. It's just convention. But if k equals 2, we have 2 classes in our classification problem. We often just use the label set 0, 1 rather than 1, 2. This is just convention to be aware of. Okay, so I showed you guys this slide maybe a couple of weeks ago. But here are just some examples of classification problems that you can handle using machine learning techniques. So for instance, you might want to take in the text of some email and predict whether or not this email was a spam email or not a spam email. So this is a binary classification problem. We're trying to predict one of 2 labels, spam or not spam. And in practice, to encode these labels into an actual data set, we would often write y equals 1 for spam or y equals 0 for not spam. So again, we're just using integers, whole numbers to sort of represent our possible labels. For some more examples of classification problems, you might want to, say, take in an image into your model and predict what type of animal was in this image. Now, this is a very sort of difficult problem because there's potentially 500 or more different labels we might be trying to predict. You can also, say, take in a speech signal corresponding to a spoken word, and you try to label that as what English word was spoken. Again, very difficult classification problem. Many, many labels we could be trying to predict. Other applications of this include, say, loan predictions. So whether or not a particular applicant is going to repay their loan or not. It's a binary classification problem. And another example is, say, medical diagnosis, where you take in some features about a patient and predict whether or not they have a disease. So here, I just really like to emphasize that classification is a very general problem. There's lots of different problems out there in the real world that fall under this umbrella of classification. And so if we know classification techniques, we can really tackle a whole host of different problems. Okay, some reminders on notation. If we go out and collect a data set, it's often very convenient for us to stick all of our data into a big matrix. So capital X is our data matrix, where every row in this data matrix corresponds to an individual data point, and every column in this matrix corresponds to a distinct feature. So again, rows might be patients in a medical data set, and columns might correspond to different features about these patients, like their height, their age, their weight, so on and so forth. So in a classification problem, we also have some associated vector of labels with our data. So boldface Y is our vector of labels in our data set, where we have one label per individual. So for example, we might have some data matrix X that looks like this, with 3 features, so 3 columns. And if there's 3 different possible labels in our data set, Y equals 1, 2, or 3, then our vector of targets, i.e. our labels, might look like 3, 1, 2, 3, so on and so forth. So this is just an example of how we actually kind of encode a classification problem into numbers that we can work with on our computers. Okay, we also saw this data set previously, this penguins data set. And we'll be using this data set throughout today's lecture just to illustrate some basic properties of classification problems. So in this data set, we've got 344 penguins, so 344 rows in our data set. Each of these penguins, we went out and collected 4 different attributes about them. So their bill length, their bill depth, their flipper length, and their body mass. And this is a classification problem because from these attributes of our penguins, we'd like to somehow predict what species of penguins we have. So our penguins could be Adele penguins, chinstrap penguins, or gentoo penguins. So we've got a 3-way classification task here. Okay, and this is maybe the first few rows in our data matrix of penguins, just to give you a sense of what this data looks like. Okay, so imagine for a second that we have a classification problem where we only have 2 features in our data set. So we've got feature 1 and feature 2. What I'm showing you here is a scatter plot of my data. So every one of these dots here represents a different data point in my data set. What I've done is I've colored each of these dots by their corresponding class labels. So here I've got a binary classification problem where every one of my dots either comes from the blue class or the red class. So this might be some kind of medical diagnostic problem where the blue class are healthy patients and the red dots are sick patients. And in this, fairly simple example, to do classification, what we really want to do is kind of separate these 2 clouds of points, right? We'd like to somehow, separate out the classes. And you could imagine just taking out your pen and drawing a line between these 2 classes. The idea being that if we fall on this side of the line, we're going to predict class equals blue for all of these dots. And if we fall on the other side of the line, we're going to predict class equals red for all of these dots. So what we've really done is drawn some kind of decision boundary where, depending on what side of the boundary you're on, we'll make different predictions for the labels of our data points. Here we have a very simple decision boundary. It's just a straight line. And in fact, if you probably sat down and thought about it for long enough, you could write down an equation for this decision boundary. But a lot of times, our classification problems aren't so easy and aren't so simple. We often can't just separate them with a line. So in practice, the decision boundary of a classification model will be a whole lot more complex than just a straight line. So far I haven't told you how to actually find these decision boundaries and what we do with them after we have them, but we'll see more about that later. But What I'd like to really emphasize here is that you can think of classification problems in this sort of geometric way of separating out your data points based on their class labels. So in the example I just showed you, we had just 2 features. And in general, the number of features in our data set is often called the dimensionality of the classification problem. So in our really 2-dimension data set that we were just looking at, it's easy enough to just plot our data points and draw a decision boundary. You know, we can kind of just look at our data and do classification that way. But in practice, for most machine learning problems, we have a whole lot more than 2 features. So for instance, a typical ML problem might have something like 100 features, 1,000 features, maybe even 1,000,000 features if you got a really big data set. And so trying to plot your data and draw a decision boundary by hand just isn't going to work for these kinds of problems. You know, how could we possibly do this? And this is really why machine learning is useful, is because we can take in these huge high-dimensional feature vectors and somehow search over the space of decision boundaries, i.e. fit some kind of model that will help us, you know, classify these data points. Even though you can't really visualize, you know, how you draw these decision boundaries in very high dimensions, the idea is the same as that kind of 2 blob example I showed you. We're really trying to separate out our classes. Okay, here I am arguing that, you know, you should think of a classifier as some kind of black box function or some kind of mapping. So a classifier is going to take in some kind of input, some kind of feature vector. It's going to do something with that information. We haven't really said what yet. And with that information, it's going to output some kind of predicted label for that data point. What you should note here is that I've written y hat instead of y. And by y hat, I mean the prediction coming from a classification model. And I'm distinguishing this from y because, you know, oftentimes our classifier might make a mistake. So here, maybe if my inputs are features about some penguin, the classifier might predict a species for that penguin, but it doesn't necessarily match, you know, the true label in our data set. So y hat means a prediction from the model, y means a true label coming from the data set. If our function, our classifier, is smooth in some kind of appropriate sense, i.e. if feature vectors are nearby one another, then they should get nearby sort of label predictions, then we can often think of what are called decision regions. So these are regions in the input space that map the same value, or map different values of x to the same label. Okay, let's see an example of what I mean by a decision region. So here I've got our penguins data set, and I'm only looking at 2 of the features of these penguins. So on the x-axis, I've got bill depth, and on the y-axis, I've got the length of the bill. And I've plotted my data points and colored them by their class labels. I fit some kind of classifier on these. I haven't told you how to do that yet. But what you can do after fitting your classifier is find these so-called decision regions. So every point in this red region corresponding to some data point will get predicted as a Gen 2 penguin. So the classifier kind of claims this red region for the Gen 2 penguins. We're going to predict Gen 2 for every point in here. And then it's the same thing for the other 2 regions. But here, you know, I'm trying to emphasize that you can really think of decision regions in this kind of geometric way, sort of partitioning the data space, and we can use that partition to predict labels for our data points. One thing that you should note here is that even though we have these decision regions, they're not perfect. Our classifier is making mistakes. So we've got some blue points appearing here in the Gen 2 penguin region, but those are really chin strap penguins. So our classifier is, you know, maybe a little bit too simple for this data set. It's not, you know, making perfect predictions on all our data points. Okay, any questions on classification problems in general? Yeah. So Yeah, exactly. So the way you actually get these decision boundaries, or these decision regions, is that you can take any point in our sort of input space, so any kind of data point, stick it into your classifier, and get out a prediction for that data point. So I might have some point here. It's some feature vector. I didn't see it in my data set, but I can still put it into my classifier. And the classifier here is going to predict Gen 2. So for every point in this space, I can make a prediction, and from that I can create these decision regions. Cool. Any other questions on classification? Okay. So before we see our first classification model, this nearest Centroids classifier, we got to go over some details on how you compute feature means and how you can compute distances between feature vectors. Okay, so the first thing we need to do before setting up our nearest Centroids classifier is that we need to be able to take the mean values of individual features. So what I mean by that is if we have some data matrix X, where the rows are different data points and the features are different columns, I'd like to take the mean value, just the average value of my second feature. So sort of visually what's happening is I can look at all the data in the second column and just take the average, add it all up, divide by n. And this gets you, the average value of whatever that feature is. So if this is like flipper length, it'll get you the average flipper length of your penguins. Here's the same thing, but in a little bit more formal notation. I'll write mu sub j for the mean of the jth feature. And mu sub j is an average, so it's a sum over all of the rows in my data set of the elements in the jth column. So a little bit of notation here, but I'm doing nothing more than averaging the columns of my data matrix. Okay, this is the same formula that I showed before. It's the mean for the jth feature in my data set. And what I can do now is compute what's called the mean feature vector. I'll denote this by a boldface mu, and oftentimes this is referred to as like a centroid. And to compute this vector mu, what I'll do is compute the mean for every one of my distinct features. So mu sub 1 is the mean of feature 1. The next entry here is mu sub 2. It'll be the mean of feature 2, all the way up to mu sub d, which is the mean of feature d. You can also write this as follows in this second equality, where we sum up the feature vectors. So this is now vector addition rather than just adding up scalar numbers, and just take the average of them. So really, in some sense, we're just taking the average of all our data points. Okay, let's look at a simple numerical example that hopefully will make things a little bit more concrete. Let's say our data matrix X has just two rows. We have just two data points. The first row is this feature vector, and the second row is this second feature vector here. To compute the mean, mu sub 1 for feature j equals 1, we just take the average of this column here. And if you do that, you'll get something like 24.75. The mean feature vector then, it's really kind of the mean of our data, means we just average all of the different columns and then collect these into a vector. So 5.8, for example, is the mean of this second column here. 172 is the mean of this third column here. So again, we're just taking sort of averages of our data. In Python, you can do this in a one-liner with some vectorized operations. So if you do numpy.mean on a data array x, and you specify the axis over which you take the mean, then you'll be able to actually compute this in just one line. So axis equals 0 tells us sort of which way we're taking the means. So axis equals 0 means we take the means of the columns. And you can really think of these centroids, or these sort of mean feature vectors, in a very geometric way. So here on our penguin data set, looking again at just flipper length and bill length, I've created a scatter plot of all my different data points. So each of these blue dots represents a different penguin. If I compute the mean feature vector, or the centroid of my data, I get this red dot here in the center. And again, the mean, or the centroid, has the same dimensionality as our original data. And you can really think of it as sort of the point that's in the middle of all my data. It's the average of all my data points. And hopefully visually it's clear enough. This red dot is kind of near the center of all my data. I can also do this on a per class basis. So rather than just computing one overall centroid, this red dot, what I've done is I've taken my data and partitioned it based on the class label. So I took all, say, the chinstrap penguins, the orange dots, and then I computed the centroid for only those penguins. So this black dot here is sort of the mean of all my orange data points. Here, all the green dots are, say, my Gen 2 penguins, and I compute their mean, I compute their centroid, that's this black dot, and the same thing for my third class. And so you can think of these centroids, these mean feature vectors, as really sort of summarizing my data, or sort of, really finding the center of my point cloud. Okay, the next thing we'll need in order to set up our nearest centroids classifier is a way to compute distances between feature vectors, or between data points. So if I have two data points, which are these two red dots, I'll call them X and Z, for example, I'd like to just be able to compute how far away these two data points are from one another. And to do so, I'll use this Euclidean distance. And this is really just the usual formula for the length between 2 points. To obtain this, I look at the difference between the individual sort of components of these feature vectors. So X sub j and Z sub j are like maybe the first component of two vectors. I'll square that difference, sum them up, and take the square root. So this is really just Pythagorean theorem in disguise. Essentially, we're computing the length of this hypotenuse here in red of the right triangle kind of formed between my two data points. So this is just, again, the usual distance formula between sort of 2 points in our space. I'll point out here that this distance formula works in any d-dimensional space. So we can use this to compute distances between sort of arbitrary data points or arbitrary feature vectors. Okay, here's some code showing you how you can actually do this in Python. Won't go over the details here, but it'll be useful in homework too, so review these lecture slides when you're working on that assignment. So the Euclidean distance is just one example of a distance function we can use. There's other ways we can measure distances that aren't that formula that I showed. And if you remember from Wednesday's lecture, we introduced this notion of an LP norm. Again, the idea of a norm is that it measures kind of the size or the magnitude of a vector. And in order to get a distance from a norm, what we'll do is we'll take the difference between our two vectors, so x minus z, and then we measure how big that distance is by taking its norm. So to get an LP distance, we simply apply this formula, which is the LP norm of x minus z. And if you expand out the definition of that, write things in terms of the components, it's this formula on the right. So we look at the difference between the components of our vectors, raise them to the pth power, sum them up, and then raise the whole thing to the 1 over pth power. So let's look at some examples, make this a little more concrete. For p equals 1, we get a distance formula called the absolute distance. And this is nothing more than the sum of the absolute values between the components of our vectors. So this is a fairly straightforward way that we can measure distances. In the case p equals 2 gives us what's called the Euclidean distance. And we saw this formula before. It's again just another way of measuring distances between vectors. In practice, p equals 1 and p equals 2 are most commonly used, but you can stick pretty much whatever value of p you would like into this formula and get a new way of measuring distances. And we'll see in a little bit how this choice of p, this distance metric, can have different effects on your classifiers. So let's look at an example in our penguin data set. Let's say look at the first 3 examples in our data set. So we've got 3 penguins, x1, x2, and x3. The distance between x1 and x2 is about 50, and the distance between x1 and x3 is about 500. So here I'm using the Euclidean distance. And if you'd like to double check that you really understand what those distance formulas are doing, you can go ahead and compute these numbers on your own, and hopefully if I didn't make a mistake, you'll get the numbers I have listed here. And I'll point out here that the distance between x1 and x3 is about 10 times the distance between x1 and x2. But here I'd like to point out that the scale of our data, or the units of our data, really going to have a significant effect on any distance calculations that we do. So, for example, notice that our body mass for our penguins is measured in grams in our data set. If we instead measure the body mass in, say, kilograms, so we divide every value in this column by 1,000, this is going to have a pretty big effect on the distances that we calculate between these feature vectors. So in this case, after changing the units of just the measurement in this column, the distance between x1 and x2 is about 5, and the distance between x1 and x3 is about 14. And so, even though x2 is still closer to x1 than x3 was, it's closer by a smaller factor. And so scale really has, a significant effect when we're computing these distances. And in a little bit, when we use these distances inside of the classifier, we'll see some pretty, serious effects of scale. And so this is really just to illustrate that, you should pre-process your data. You should always scale it before using a classifier. Okay, and I've mentioned this a little bit already, but I'd like to emphasize that in machine learning, it's generally useful to try and think of things in, a very geometric fashion. So instead of thinking of data points as, lists of numbers corresponding to, patients or something like that, it's very useful to think of your data points as actual points in some space. We have some point cloud of data. When you think of data in this way, it's very natural to think of things like distances between points, like we had already seen. You could think of, say, clouds or clusters of points. We'll see clustering methods later on in the course. And of course, you can also think of things like decision boundaries that separate these points like we had already done. Again, my point is just, keeping these geometric concepts in mind is a very useful way to think about ML problems. Okay, any questions on computing feature means, distances, anything like this? Yeah. Yeah, so imagine you have two feature vectors that have just two different features. So maybe it's flipper length and bill length. You can imagine plotting these in a 2D plot like this. So we'll get a red dot and another red dot for our two different feature vectors. And then the distance is really just the straight line distance between those 2 points in this 2D space. If you have a higher dimensional feature vector, you can't really plot the points, right? How do you plot a 4D point? But it's the same idea. It's the distance between these 2 points living somewhere in some kind of space. So here we're not averaging features, it's individual data points. So this is a penguin, this is another penguin. How far away are the features for these penguins? Yeah, so if we have one penguin and we have another penguin, we can compute their distance. And we can do this for any two pairs of penguins. Cool, any other questions? Yeah. Yeah, exactly. So for the purposes of illustration, I'm showing you the distance between two-dimensional feature vectors, but this formula works for arbitrary number of features. Yeah, another question. So for very large values of p, the p norm is very close to the maximum difference between the feature values. So let's say you have a feature vector that corresponds to someone's age, their height, and their weight. If you use a very large value of p, then the LP distance for large values of p is close to the sort of maximum value of xj minus zj. So maybe, we can compare features by how sort of large the biggest difference in a particular feature is. In practice, P can be a hyperparameter in your model, and it's something you can tune with experimentation. Okay, let's move on to the next section in today's lecture, which is the nearest centroids classifier. So this is our first classification algorithm of many. We'll see a whole lot more. This is a very simple algorithm. Doesn't get used all that much in practice, but it's very intuitive and has a very nice way of thinking about it. And it's a good introduction into classification algorithms. So in order to actually compute the nearest centroid classifier, what we're going to do is we're going to take all of our training data, and we're going to separate it based on the classes. So I showed you guys this graph before, but what I've done is I've separated out my data based on the species of penguin that it is. Now I've computed the centroid for every one of these classes. So I've got 3 different centroids, each kind of representing a class. To make a prediction for a new data point, so I didn't see this data point here during training, it's a new penguin that I'd like to predict a label for. What I'm going to do is I'm going to compute the distance between this new penguin, its feature vector, and each of the 3 class centroids. So I'll compute the distance between this gray dot and the orange class centroid, the distance between the gray dot and the green class centroid, and the same thing for the blue class centroid. And then whichever centroid is closest to my gray dot, that's the label that I'm going to predict for this unknown data point. So in this case, probably the orange point is closest to the gray dot, and so I'll predict chin strap for this new data point. Question, yeah? Then you are on the decision boundary, and you got to guess which one is closer. Yeah. Okay. So, yeah, this is a very simple idea for doing classification. There's no sort of real learning that's going on, right? All we have to do to implement this algorithm is compute these 3 centroids, and then compute the distance between a new data point and these centroids. So, fairly simple. This is, a pretty plausible idea, though. And sort of the intuition for why this might work is that the centroids are kind of templates for a class, They represent, okay, what's the average chin strap penguin like? What's the average Gen 2 penguin like? And then to make a prediction for a new penguin, we just see how far away it is from those average penguins kind of representing each class. Okay, so for an example, I've gone ahead and fit the nearest centroid classifier on my penguin data. Here I'm just looking at 2 features to keep things simple so we can actually visualize things. And each of these black dots is the centroid of each particular class. And so what you can see is that the nearest centroids algorithm kind of partitions our data space into distinct regions corresponding to distinct predictions. So if I have a new penguin, say, up here where my pointer is, the closest centroid to this point is this guy, and so we'll predict Gen 2 for this penguin. But if we have a data point out here, it's of course closest to this centroid, and we'll predict chin strap for that penguin. Bit of a side note on how we actually kind of plot these decision regions and these decision boundaries. There's kind of 2 approaches to how you can actually create plots like this. The first is if you have a really simple classifier, like the nearest centroids, you can often mathematically solve for the equations of the decision boundaries. And by the decision boundaries, I mean these lines here that kind of separate the decision regions. Any point on these lines are points where the distance between 2 centroids is equal. So if I'm on this line, the distance to this centroid is the same as the distance to this centroid. And so it's kind of the line that separates these 2 decision regions. And yeah, if your classifier is simple enough, you can actually write down equations for these lines. And in the next lecture, we'll see how you might actually do that. A more simple way, kind of more practical way of doing this, is you can create a dense grid of inputs. So I can make a grid on this plot corresponding to a whole bunch of different feature values. I can plug them into my classifier and make predictions for those data points. So for, say, a data point here, I'll get some kind of prediction, and then I can use that prediction to create these decision regions. Okay, I've got some pseudocode here showing you, the steps you actually need to take in order to train a nearest Centroids classifier. I'm mostly showing you guys this because in homework 2 you'll be implementing this nearest Centroid classifier. So it's good to see a little bit of an in-depth explanation of how this works. So to sort of train our nearest Centroid classifier, the first step is to compute the different number of class labels we have in our data set. So this is how many labels that we could potentially be predicting here. One thing I'll note is that there's a small typo in this pseudocode. We previously were using capital K to represent the distinct number of classes, but in this pseudocode I'm using capital C. It's again just the different number of classes we have in our problem. Okay, once we've found the number of different classes in our problem, what we're going to do is loop over each of these classes. So for example, we're going to start with all the data points whose label is 1. In these 2 lines, what I'm doing is I'm getting all of my data whose Y value is 1. So maybe I get all of my data points corresponding to my Gen 2 penguins. Then I calculate the centroid for all of those penguins, which you can do using the formula I showed a few slides ago. And that's it. We do this then for every one of our different centroids, and just return that list of centroids that we compute. So again, all we're doing is computing these black dots on a sort of per class basis here. In terms of making predictions with the nearest centroid classifier, all we need to do is loop over each of those class centroids and figure out which one is closest to our new data point x. So here x is some new penguin, some new data point that we don't have a label for, but we would like to make a prediction for this data point. So we can start out by initializing, say, the minimum distance to minus infinity, and then loop over all of our class centroids, compute the distance, say the Euclidean distance in this case, between that new data point and the centroid for class C. And if this distance is smaller than the minimum distance that we've already found, we can set our prediction, i.e. the class label we're predicting for this data point x, to be C. And at the end of this for loop, we just return that minimal distance prediction. So, here's a question? All right, cool. Well, anyone else have questions on near centroids? Yeah. Yeah, so the question is, what do you do if you're on the decision boundary, if there's 2 centroids that are equally close? In practice, this is very rare to happen. Like, you have to land on a very, very specific point. But if you are in that case, oftentimes what you can do is sort of flip a coin. So if it's equally close to the centroid for class 1 and class 2, you can say, okay, I'm going to flip a coin and choose class 1 with probability 1/2 and class 2 with probability 1/2. I think that's probably the most common thing to do because we sort of are equally likely to be in either one of these classes. In general, you don't want to return multiple predictions for a data point unless you kind of have a good reason to do so. Yeah. So the dense grid prediction, what we do is we essentially make a grid in this 2D space, and every point in that grid is like a new test data point that we kind of make up. So maybe one point on the grid is here. It's like having a feature vector, having a data point at that grid point. We can put that into our classification algorithm and get out a prediction for this kind of made up data point. So for here, the classification algorithm predicts Gen 2 penguin. But we can now do this across all the different grid points, right? And so we can get a prediction sort of everywhere in this space. And then using those predictions, you can create the colors and create the decision boundaries. Yeah, another question? Yeah, so this is definitely not an optimal classifier by any means. So the nearest centroid classifier is just a very simple classification method. We'll see much better models later on in the course, but yeah, you're right, this classifier isn't doing all that well. It's making lots of errors. Okay, cool. So again, in homework 2, you'll be implementing this nearest centroid classifier. Okay, and then with about the 10 minutes left we've got in class, we're going to briefly talk about how you actually evaluate classifiers. So let's say you went out, collected some data, fit a classifier to this data set. How do you tell how well your model is doing? And for a second, let's forget about nearest centroid classifiers and just say we have some classification algorithm. For the purposes of evaluation, it doesn't matter too much what is going on sort of internally to this classifier. All that matters is that it's taking in inputs and making predictions y hat. The simplest way we can actually evaluate a classifier is to just compare that predicted output, y hat, to the true label y in our data set. So if y hat is equal to y, i.e. our model makes a prediction that agrees with the true label in our data set, well, the accuracy of our model is then 1, it's 100%. It gets a point, it made the right prediction. If the labels disagree, then the model made an incorrect prediction, and we'll say the accuracy is 0. It got this example wrong. In terms of a little bit more formal notation here, this accuracy is really kind of a function that I'll call I, which is an indicator function. So the indicator function takes in y hat, a predicted label, and y, a true label, and it returns 1 if the arguments are equal, so the model makes a correct prediction, and it returns 0 if the model makes an incorrect prediction. Okay, so this is how we evaluate the accuracy of a classifier on an individual data point. But of course, we don't really care so much if it's doing well on a single data point. We care how well it's doing sort of on all the possible testing examples. And so what we can do is we can look at, say, a validation set or a testing set, which we saw the details of in the model selection lecture yesterday, Wednesday. And let's say we have, say, n test examples in our testing set. The accuracy on the ith data point, i.e. Whether or not the model predicted correctly on data point I, is just this indicator function comparing y hat I, the model's prediction on the ith data point, and the true label y sub I for the ith data point. The average accuracy, then, is we just sum up all of these individual accuracies and divide by the number of total testing points. So, in other words, all this is calculating is what proportion of my testing points did the model correctly classify. Okay, let's look at an example. So let's say this is our data matrix. We've got something like 4 different data points. The model takes in these data points and makes 4 different predictions, 1 for each data point. So for the first data point, it predicts 0. For the second data point, it predicts 0. It predicts 1 and a 1. And let's say we also have the true labels for these data points. These are the actual species of our penguins. We can then compare the predicted labels to the true labels and just essentially average how often our model gets things right. So the model makes a correct prediction on the first instance. It predicts a 0 when the true label is 0. So it gets a kind of 1 point for that example. On the second instance, it makes an error. It predicts y equals 0 when the true label is y equals 1. So it gets 0 points for this one. And then it correctly predicts the last 2, so it'll get 2 points for those. So the overall accuracy then is about 3/4, 75%. I'll point out here that we also often look at what's called the error rate of our classifier. And this is nothing more than 1 minus the accuracy. So clearly we want high accuracy for our classifiers, which is the same as having a low error rate for our classifiers. Doesn't really matter too much how you actually express this accuracy. It could be a fraction, decimal, percentage, whatever you like. Okay, so let's look at an example of the accuracy of a nearest centroids classifier, again on our penguins data set. So I fit my nearest centroid classifier on 200 data points, and then I'm evaluating it on a held out test set of 133 data points. And what you can see is that, it's not doing very good. It's got an error rate of about 13%. So, maybe this isn't the best classifier for this data set. One thing I'd like to point out here is that the scale of our features is quite different. So the flipper length is between like 170 and 230, so a pretty wide range. Whereas the bill length feature is between about 30 and 60, so a much smaller scale for this feature. And as I pointed out before, the way you scale your features has a pretty big impact on these distance calculations. And in the nearest centroids classifier, those distance calculations between the centroids is really what we're using to make predictions. And so essentially what's happening if our features are on different scales is that they're essentially being up-weighted or down-weighted in that distance calculation. So oftentimes it's quite important to actually scale your features before feeding them into a prediction model. Okay, so one way we can scale features, this is an alternative method to that standard scaling method I showed you guys a little while ago. It's called min-max scaling. It's a little bit simpler than the sort of standard scaling we talked about before. But what we do is for every feature, we look at the minimum value of that feature, we subtract it from a particular data point, and then we divide by the maximum value of that feature minus the minimum value of that feature. So all we're doing is we're taking our data and squashing it so that it's all between 0 and 1. We're just rescaling stuff. And what happens if we do that and then fit our nearest centroid classifier is that our error rate drops to about 5%. So we got about a 5% boost in accuracy by just scaling our data points. And again, this really goes to demonstrate that the way you pre-process, the way you scale your features can have a huge impact on model performance. This error rate here is, of course, with only 2 features, so the flipper length and the bill length. But if you use all 4 features and scale all of them, we can get our error rate down to about 1.5%. So nearest centroids does pretty good on this data set if we pre-process our data and actually use all our features. That's not to say nearest centroids is a good classifier. It's more so saying this penguins data set is quite simple. I'll also point out that the data you have really, really matters for the performance of your classifier. So if we only look at the build depth and the body mass, for example, what you can see is that these points are not well separated when we only look at these 2 features. So we can separate out the blue points pretty well, but the green and the orange points are now overlapping in this different feature space. And so really the performance of any classification method highly dependent on your data and how you represent that data. Okay, and I think in the interest of time, we'll move this to the next lecture. So let's just quickly summarize and wrap up what we talked about today. So we started looking at classification problems, and these are prediction problems, supervised learning problems, where we're trying to predict some kind of discrete label. We can compare this to regression problems, which is what we had been looking at, where in contrast, we try to predict a real valued number. And the techniques for regression and the techniques for classification we'll see are quite different from one another. I also pointed out various different geometric concepts in machine learning, i.e. thinking about data as points in some kind of space, and then we could think about sort of norms, i.e. size of vectors and distances and centroids, these very geometric ideas. And then lastly, we